The last thing we're going to talk about here is titrations. And titrations are a powerful tool for a chemist. And here at Mount Hood, when we do a titration, we can compete with MIT and Caltech and all these places because with this simple equipment, we can actually do some pretty serious research, which is kind of a cool thing into itself. But anyway, we're going to talk mostly in this section about acid and base titrations. And this is how you can find out what the concentration of your reactant is, or maybe even find what the molar mass is, stuff like that. But in order to do that, you need a titration curve, and the titration curve will come from a pH meter. Indicators work, but honestly, they're kind of cheesy, so I don't recommend them. So pH meters, which is what we'll try to use, are used to determine when the solution has reached the equivalence point. And earlier we talked about what happens when the moles of acid and the moles of base are the same. Equivalence point is an important part of a titration. So in a normal titration, what you have is like on the picture on the right, you have what's called a burette, which is a long, narrow tube that allows you to accurately control how much of a liquid goes into your solution. And the pH meter will monitor the pH effects that are happening. So in this example, you're adding sodium hydroxide to HCl. So the pH meter starts by reading acidic pHs. You can see it reads 1.30, but as you add more base, that pH will start to jump. And knowing how acids and bases work will make titrations a lot more helpful for you too. This is an example where you're adding sodium hydroxide, probably to acetic acid. And you can see how there's different combinations here that are happening. So the first amount of acetic acid makes the pH go up just a little bit. The second amount of sodium hydroxide, though, makes the pH up go quite a bit until you reach that point right there, which is the equivalence point. And finally, the sodium hydroxide makes the pH go up a lot, and you finally begin to kind of level off once you get to the pH of the sodium hydroxide. So this is kind of an example of a titration. And notice on the far right, it's kind of like an S. So sometimes they call them S curves. And on an S curve, which you definitely see when you have an acid that you start with and you add a base to it, the equivalence point, the steep point in that titration, that's going to be a real important part for chemists. That equivalence point, the midpoint of the steep part there, is where the moles are equal. So as you add a base, the pH will rise, but then finally it's going to level off once you get past equivalence, because then you essentially have only the strong base, sodium hydroxide, to deal with. Eventually it will get very, very close to the concentration of your pure sodium hydroxide.
When a molecule of hydrogen chloride and a water molecule encounter each other, they react to form a hydronium ion, H3O+, and a chloride ion. When sodium hydroxide enters the solution, it splits into sodium and hydroxide ions. The hydroxide ion and the hydronium ion react readily with each other to form two molecules of water. Sodium and chloride ions are left in solution.
If you want to figure out mathematically what the pH should be for a titration, it is possible. And generally what happens is titrations are split up into 4 regions. The initial point, where in this case you only have a strong acid. You have an equivalence point, where the moles of what you're adding, in this case a strong base, equal the moles of what you started with, the strong acid. Then you have the pre-equivalence region. Moles of what you started with are greater than what you ended with. And finally, you have post-equivalence, where the moles of what you're adding are now greater than the moles of what you're starting with. So in a titration, the first thing listed, in this case strong acid, that's what you're starting with. So in this problem, you can see how the pH down here is acidic. It's the pH of a strong acid. But we're slowly adding in the second part. You're adding here a strong base. So overall, this pH is getting more and more basic. So understanding this then allows you to calculate the pH at any range. Now, N stands for moles, and it comes from PV equals nRT, the gas law, even though these aren't gases. N stands for moles. So moles of strong acid, NSA, moles of strong base, NSB. One more thing, at equivalence between a strong acid and the strong base, you have nothing left that's going to affect pH except water. So the pH at equivalence point should be pretty close to pH of 7, and that's what we're going to see here. We're going to compare that here in a little bit to a weak acid strong base. Those have different pHs at equivalence, but if you have to identify what your acid is, if that pH is about 7, you've got a strong acid. So in this question, it says at equivalence, the pH of a strong acid, strong base titration should be, and it gives you the three choices: less than 7, i.e. acidic; greater than 7, i.e. basic; equal to 7, neutral; or maybe it depends on the concentration of the acid or the base. Okay, so equivalence means the moles are equal. So this means the moles of strong acid equal the moles of strong base. And like we just talked about, and this is pretty important, at equivalence, your pH should be 7, because you have nothing left when the moles are equal that's going to affect pH except water. We talked about how the conjugates of strong acids and strong bases don't affect pH, so you'll have things like NaCl and water, or KNO3 and water, and none of those things affect pH. That's why the pH is going to be 7. If you have a strong acid, strong base titration, you can figure out the pHs of these different points. And we're just going to kind of gloss over them here. But if you're curious, definitely reach out to me. I can tell you more. Initially, you only have a strong acid, so your pH is going to equal the minus log the concentration of the acid, or moles of strong acid divided by volume of strong acid. This is a nice way to do it because later we'll use the NSA value, the moles of strong acid, in the calculation. Now at the pre-equivalence region, you have more strong acid than you have strong base. So you need to figure out essentially how much extra strong acid you have, and that's what the numerator is saying there. You're going to subtract the moles of strong base from the strong acid to find out how many moles of strong acid are left. And in the denominator, the bottom down there, you want to divide by the total volume of the solution in liters. Now VSA and NSA won't change because you're not changing that, but you will change the amount of strong base. So that's why NSB and VSB will change. But if you calculate them, you can find to amazing accuracy what the pH will be at those points. Now finally, you'll get to the equivalence point. And in this particular problem, it looks like it's about 50 milliliters. And at that point, moles of strong acid equal moles of strong base. You're only going to have water and some neutral salt, which doesn't affect pH. So that's why the pH should be very, very close to 7. So just keep that in the back of your mind. Now, once you get past equivalence, now the strong base dominates. You're going to have more moles of base than acid, so you need to figure out how many extra moles of base you have, and that's what the top part is saying. And remember that 14 plus log hydroxide is one way to calculate the pH of a strong base. Well, that's basically what we're doing here. We're finding the moles of strong base that are left over, dividing by the total volume in liters. That's what the bottom is. You can find the pH at any point in a strong acid plus strong base titration.